Everybody, Dr. A here, and in this video we're going to be exploring another example of angle of twist. So let's go ahead and get started. In the given information, we're being asked to compute the angle of twist of the free end with respect to the fixed end. We're being told the shear modulus is 3500 KSI, and we're already directly given the polar moment of inertia as 8 inches to the fourth. So here we have this 3-foot long shaft. The free end is at A and the fixed end is at B. And we have a uniformly distributed torque load spread out over the length of the shaft. It's a uniformly distributed torque load, and that's equal to 0.5 kip feet per feet. And if you notice here, we have a little origin and an x-axis pointing towards the fixed direction, okay? Now, how do we solve this? Well, the first thing we need to recognize is we're going to have to use the integral version of our angle of twist formula. So I'm going to make a note here. I'm going to say use integral version of phi. How do we know that we have to use the integral version? Well, we know that because of the presence of this uniformly distributed torque moment. Remember, phi has T, which is torque, in the numerator, but we don't have T directly given to us, right? I mean, think about it. If you use method of sections and you make a cut anywhere along this shaft, T is going to be changing. So let's make a note of that, okay? T is changing throughout the shaft's length, okay? Think about it. If you make a cut here, if you make a cut here near the end, that internal torque that's here near the end is going to be this uniformly distributed torque moment multiplied by that little distance. Well, if you were to cut closer to B, the magnitude of capital T here is going to be this uniform torque times this longer distance. So T is changing throughout the length of the shaft. In particular, it's changing linearly. So how do we get what T is? Well, we could either use method of sections or we could draw an internal torque diagram. All right, so I'm going to say by method of sections, just to show us what that looks like, I've got the free end here, and I make a cut here, and I'm making a cut at what distance? Well, I'm going to cut it at distance x, okay? Not 1 foot, not 2 feet, not 3 feet, but at x feet. So x is represented by this variable, and so x represents a cut at any point along the length of that shaft, okay? And so on this little nub of the shaft in our free body diagram, we've got the 0.5 kip feet per foot, okay? And then what we have here is an internal torque here showing up at the cut, and we can draw our little viewpoint here. And when we look at that viewpoint, inside of that viewpoint, what do we see? Well, we're going to see maybe a circular cross section, all right? And we see T that we're looking for. And then behind T, behind it, what do we see? We see that 0.5 kip feet per foot. All right? And so how do we get what T is? Well, we're going to say sum of the torques equals 0, counterclockwise positive, okay? And we're going to say T minus 0.5 kip feet per foot times x equals 0. So this x right here is the length x right here in this drawing, and that's the length that the 0.5 kip feet per foot is spread out over, all right? And so we do some rearranging, and of course we get t equals 0.5x, okay? Now, what are the units of capital T? Well, this function collectively has units of kip feet, and we know that because x is a length that x itself carries units of feet. So you would have units of feet here with x that cancel with the per foot here. So we know collectively T should have units of kip feet or just torque, okay? And again, it's based on these figures, it's going counterclockwise, which indicates positive, all right? So what do we do next? Well, that's the majority of the work. That's all we really got to do. Now, if you want to look at another way of getting this T value, again, I mentioned a few minutes ago, you could draw an internal torque diagram, and you could draw your x-axis here. I'm sorry, let me draw that a little bit differently. You could, yeah, actually you could do it this way. That was the best way of doing it. I don't know what I was thinking. So T, X, feet, all right, and then you would see that, you know, you would have a torque diagram that maybe looks something like this, okay? And so it would be linear, all right? Linear, and what's the equation of this line? It would be T equals 0.5x. So that's another way of visualizing that, okay? And then, of course, this end point right here is 3 feet. And what would this high point back here be? Well, that would just be the 0.5 times 3, which is 1.5 kip feet, if you wanted to use the torque diagram. I think for this application, method of sections is better, okay? So I would prefer method of sections, but you might see a book or another reference that uses a torque diagram here, all right? But again, I would use this method of sections. Regardless, what do we do next? Well, we're going to say phi of A with respect to B, so that means the angle of twist of the free end A with respect to the fixed end B. This is going to be the integral from 0 to L of T as a function of X over J as a function of X, G as a function of X, dx. But you know, a lot of this is constant, right? JG in particular is constant. So what we really have is 1 over JG integral from 0 to L of T as a function of X dx. All right, now do we have all of these values? Yeah, absolutely. So we're going to say phi of A with respect to B is equal to 1 over 8 inches to the 4th times 3,500 KSI multiplied by the integral from 0, and I'm going to go to 36 inches instead of 3 feet of 0.5x dx. Now, why am I going to 36 inches? Well, I've got 8 inches to the 4th and 3,500 KSI, so I've already got units based on inches here. So if I integrate from 0 to 36 inches, which is, 3 feet converted to inches, it'll all work itself out. And the reason is because this term, 0.5x, that's a torque, right? And it's going to, right now, it collectively has units of kip feet, right? But the feet, the kip feet, is being represented by this x, and then when you multiply it by the equivalent of L, which we're doing by integrating, and we have dx here, that's going to incorporate the TL together in the numerator. Now, converting that 3 feet to 36 inches incorporates that conversion factor of 12 inches by putting it in this upper limit. And so it's going to get inserted into this x during the integration process, right? And so when we integrate this, it really becomes 0.5x squared over 2, or 0.25x squared. So the conversion of 12 inches per foot gets built in, and then it gets squared, right, by the essence of taking the integral here, all right? So we integrate this, and we can, take this integral by hand, or we can, do it in our TI-36X Pro calculator, and we perform the integral. We don't forget that we need to incorporate in that 8 times 3,500 in the denominator, and so what we're going to get is a positive 0.0116 radians, and that's going to be a counterclockwise rotation, which makes sense. I mean, if you look back at the original figure, no matter how you look at it, when you look at this viewpoint here, you have T is going counterclockwise, or if you just look at it from outside here, you have this twisting going counterclockwise. So the angle of twist makes sense that it's going to be a counterclockwise type of rotation. So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for similar content. Thanks for watching.